quick question. When a nucleophile attacks a chiral carbon and kicks out a leaving group, does the product's configuration invert or stay the same? 5 seconds. Go. The answer depends on the pathway because not all substitutions follow the same rules. In this video, you'll learn what a nucleophilic substitution is, the two main mechanisms, SN2 and SN1, how Walden inversion fits in, and how to predict products, rates, and stereochemistry on real examples. To start, a nucleophilic substitution occurs when a nucleophile, nu- replaces a leaving group on a carbon. R-Lg plus nu- gives R nu plus Lg-. Here, the key players are the nucleophile, the electron-rich attacker, and the leaving group, which must be stable enough to depart. From there, substitution can proceed in two classic ways. In the SN2 pathway, the process is concerted. It happens in one step with a backside attack and a single transition state. So the rate depends on both the nucleophile and the substrate. By contrast, in the SN1 pathway, the process is stepwise. The leaving group departs first to form a carbocation, and only then does the nucleophile attack. As a result, the rate depends only on the substrate. Same overall substitution, but with very different timing. Now, let's look at an SN2 example. Take the S form of 2-bromobutane reacting with cyanide ion. The product is 2-methylbutane nitrile plus bromide. Because SN2 attacks from the back, the stereocenter flips, the classic Walden inversion. This reaction works best with a strong nucleophile, a good leaving group, and minimal crowding at the carbon. However, a common misconception is that SN2 works on any alkyl halide. In reality, tertiary carbons are too crowded for a backside attack. And it's not just the substrate, solvent matters too. Polar aprotic solvents, such as DMSO or acetone, enhance SN2 by keeping nucleophiles naked. In contrast, polar protic solvents like water or ethanol stabilize ions, which often tips the balance toward SN1. So far, we've defined nucleophilic substitution, compared SN2 and SN1, and seen how factors like substrate structure, nucleophile strength, leaving group ability, and solvent all work together to decide which mechanism takes over. Curious how much you're remembering? Your personalized practice test, flashcard set, and study guide are all waiting for you. Just tap the link now and keep watching. Future you will thank you. Now, here's an SN1 example. Let's look at tert-butyl chloride in water. First, the chloride ion leaves, forming a carbocation. Next, water attacks, and after deprotonation, the product is tert-butyl alcohol. Additionally, there are special cases worth noting. Allylic and benzylic positions stabilize carbocations through resonance. That's why even primary allylic or benzylic substrates can undergo SN1 rapidly, while an ordinary primary halide still favors SN2. Finally, keep an eye on the competition between substitution and elimination. Strong, bulky bases at higher temperatures often drive E2, an elimination pathway, instead of substitution. By contrast, weaker or less basic nucleophiles under milder conditions tend to favor substitution. So, if your prediction keeps yielding alkenes, it's a sign that E2 conditions were at play. Let's pull the pieces together with a quick roadmap. First, look at the substrate. Methyl and primary carbons usually favor SN2, while tertiary carbons go SN1. Next, think about the nucleophile. Strong, small ones drive SN2, while weak or neutral ones fit SN1. Solvent also plays a role. Polar aprotic solvents like acetone boost SN2, while polar protic solvents like water or ethanol favor SN1. Finally, check the leaving group. Iodide, bromide, Chloride and tosylate are good, while fluoride and hydroxide are poor unless activated. To recap, nucleophilic substitution is when a nucleophile replaces a leaving group. SN2 proceeds in one concerted step, with backside attack and inversion of configuration, while SN1 unfolds in two steps through a carbocation and often produces racemization. By weighing substrate, nucleophile, solvent, and leaving group together, you can confidently predict whether the reaction will follow SN2 or SN1. Ready to quiz yourself with the content covered in this video? Check out the link in the description where you'll find Quizlet content made just for you.